Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to provide an overview of classification. We're going to describe several classification models that fall under two main categories, generative and discriminative. Generative models include Naive Bayes and Gaussian discriminant analysis. Discriminative models can be separated into linear and nonlinear. Linear discriminative models include logistic regression and softmax regression, which are unfortunate names for models that are for classification instead of for regression. And nonlinear discriminative models include neural networks and tree-based models. At the end of the video, we will also discuss how to evaluate classification models. Remember that this is an overview. If you want more details on any of these topics, you can take a look at the individual videos or at the book. Let's get to it. So we're going to provide an overview of classification. Classification is the task of assigning a class to some data based on several features. Let's take a look at some examples that we will be using throughout the video. Here we want to perform Alzheimer's diagnostics. We want to distinguish between two classes, healthy and Alzheimer's, based on two features which are represented here in the y-axis. This is the volume of the entorhinal cortex, which is a brain region. This volume can be measured from MRI scans, and this is the volume of the hippocampus. These are two brain regions that are associated with Alzheimer's disease. We see that the healthy patients tend to have larger volumes, and the Alzheimer's patients tend to have smaller volumes. We want to develop a model that automatically diagnoses Alzheimer's using these two features. Another example that we will be using is distinguishing between wheat varieties from properties of the wheat seeds. So this property is called the asymmetry coefficient, and this property is called, well, it's just the area of the seed. Both features are standardized, they're centered and divided by their sample standard deviation, which is why you see negative values for area, in case you're wondering. And our goal is to separate the seeds into three varieties: Canadian, which are this kind of seeds; Kama, which are this kind of seeds; and Rosa, which are this kind of seeds. Again, automatically based on these two features. We're using several examples with two features because they're much easier to visualize. Usually, you will apply classification models to problems where you have access to more than two features. And here is an example of a problem with more than two features. Here we're using a data set from the US House of Representatives in 1984. We want to predict the political affiliation of the representatives, essentially distinguish whether they're Republican or Democrat from their voting record, which includes 16 issues. So whether they voted yes or no on 16 different issues. So we have 16 features from which to perform classification. Let's take a look at a probabilistic, at how we model classification probabilistically. We define a random variable y. It has this squiggly line on top because it's an uncertain quantity. We model it probabilistically as a random variable. And we model the features as a random vector x, where the number of entries in x is going to be equal to the number of features. Each entry is going to be associated with a feature. The maximum a posteriori estimator of y given x is the one that is basically the class that is most likely given a fixed value of x. So if we observe that the random vector x has this fixed value, we take a look at the conditional probability of each of the classes for that conditioned on that specific value of x, and we choose the one that is most likely. That is called the maximum a posteriori estimator of the class given the features. Why am I bringing this estimator up? Because it turns out that this estimator is absolutely optimal. If we know the joint distribution of the class and the features, we can actually perform optimal classification with respect to the probability of error. I have not proved this in any of the other videos, so let me do it here quickly. The proof is also in the book. We're going to assume that the features are discrete, but essentially the same proof goes through for continuous features. So what I'm going to show you is that if you have any other estimator x that maps the features to the class, then the probability that we are right, that we are correct, that the class is indeed equal to the estimated class obtained by plugging the features into this estimator X, that probability is always smaller or equal to the probability that we are right if we use the maximum a posteriori estimator. Equivalently, the maximum a posteriori estimator minimizes the probability that we make a mistake. Let's take a look at why this is the case. We're going to take this probability and we're going to apply the law of total probability to decompose it into different probabilities depending on the value of the random vector X. And then we're going to apply the chain rule. So here by the chain rule, we have the probability that the random vector is equal to that specific value, and then the probability that we don't make a mistake if the random vector is equal to that specific value. Now realize that this is the conditional PMF of the class given this value of the features evaluated at h of x. So let me show you a bit more cleanly. This is the conditional PMF that contains the conditional probabilities of the class given the features for that specific value of the features x. But the way we choose the maximum a posteriori estimator is so that it maximizes this quantity. It is the value that when we plug it in here maximizes this, right? It maximizes the conditional probability. This is precisely how we choose the maximum a posteriori estimator. So this is always going to be smaller than this because this guy is chosen to maximize this quantity. And now we can essentially take the steps in the opposite direction by the chain rule and the law of total probability. This is just equal to the probability that we are correct if we choose the map estimator. So we have shown that we are always going to be more, or at least as likely to be correct, and usually more likely to be correct, if we choose the map estimator rather than any other estimator. I feel that I phrased that in a bit of an awkward way, but the point is that map estimation is completely optimal for classification. So then you might wonder, are we done here? I mean, I can just estimate this conditional, this map estimator using the conditional probabilities that I can estimate from my data set, and I can do optimal classification. So, why do we need all of these classification models? Well, we're not, and let's see why. Let's take a look at prediction of political affiliation, where we have 16 binary features which indicate whether a representative voted yes or no for each of the 16 issues that are in our dataset. Now, if we want to compute the map estimator, we need the conditional probability of the two classes, which are Democrat and Republican, given every possible value of the 16 binary features, because otherwise we won't be able to generate an estimate, because we need to generate an estimate for every possible value of x. So can we do this? Well, in order to do that, again, we need to generate an estimator for every value of x. That's kind of easy as long as we have enough data, right? Because then we will go to the dataset and say, oh, for this value of x, what's the fraction of Republicans? What's the fraction of Democrats? And that's going to give us the conditional probability of Republican or Democrat given that value of x, given those 16, that voting pattern with 16 votes. So what are the possible values? Well, a representative has two options for their first vote. They have two options for their second vote. So we have to multiply 2 times 2 to see the number of different possibilities. Then two options for the third vote, and so on and so forth. So there's 2 to the 16 possible different voting patterns. That is equal to 65,536. And now we run into a problem because in our data set, there are not that many representatives. In our training data set, we have 425 examples. So it's going to be absolutely impossible to compute this conditional probabilities given our training data, and realize that here we only have 16 features and they are binary. If each of the features have different possible values, or we have more classes, or the features are continuous, this only becomes worse. So in general, we're not able to compute these conditional probabilities of the class given the features in a naive way unless we have a very, very small number of features. That is an instance of the curse of dimensionality. And because of that, we need additional assumptions to develop tractable classification models. And in this video, I'm going to describe the two main strategies to achieve this, which are generative models and discriminative models. And afterwards, I will discuss how to evaluate the models once we apply them on data. Generative models take the following strategy to try to approximate the conditional PMF of the class given the features. Because we've seen that this is a very good idea. If we manage to approximate it well, we're going to get a good estimate, a good classifier. The idea is to use data to approximate the PMF, the marginal PMF of the class, which is kind of easy. This is just going to usually be the fraction of data that belong to each of the possible classes. And this is going to be trickier, as we will see in a moment. We also estimate the conditional PMF if the features are discrete, or the conditional PDF if the features are continuous, of the features given the class. Once we have those objects, then we can just apply Bayes' rule to compute the conditional probability of the class given the features. This is the formula when the features are discrete. This is the formula when the features are continuous. But there's a challenge here. Approximating the conditional PMF or PDF of the features given the class is actually not obvious, and we run into the exact same problem that I mentioned a moment ago. We run into the curse of dimensionality because these are conditional joint PMF of all the features. And as we have seen, the number of possible feature vectors that we will encounter explodes exponentially when we have more than just a few features. So this is going to be in general intractable unless we make additional assumptions. In the case of naive Bayes, the assumption we make is that the features are conditionally independent given the class. In the case of Gaussian discriminant analysis, the assumption we make is that the features are conditionally Gaussian given the class. These are two different strategies that enable us to estimate these probabilities in a tractable way, probabilities or probability densities in the case of Gaussian discriminant analysis. So let's take a look at an application of naive Bayes to the prediction of political affiliation, just to make these ideas clear. So we're going to have two classes, Republican and Democrat, and we are going to have 16 features that are equal to 0 or 1 depending on whether the representative voted yes for a certain issue or no. So now when we want to apply naive Bayes, we're going to assume that the votes are conditionally independent given affiliation. This is of course not completely true, but we need some kind of assumption to get a tractable model. In that case, now the conditional joint PMF of the features given each of the classes, in this case this is given Republican, factorizes into the product of the marginal PMF of each feature given the class. And this is super important because here there's 2 to the 16 different possible values of x. Here, for each of these guys, there's just 2 possible values of each of the votes. So we can just estimate these individual probabilities individually. That was amazing, right? Individual probabilities individually, but you get the idea, and fit our tractable model, having made the sacrifice of not incorporating additional interactions that are not explained by affiliation between the votes. The same happens when we condition on Democrat. So now if we want the conditional probability of the class given the features, which is what we're interested in, for example, the probability of a representative being a Republican given their voting pattern, what we do is we just apply the definition of conditional probability. We expand the denominator using the law of total probability, and now we plug in our assumed, like our assumption, which is this conditional independence assumption, which enables us to tractably compute these conditional joint PMFs of the features given each of the classes. The estimated probabilities that we need, just to be very clear, are just the probability of each of the classes. So here there's, at that time in Congress, there were 38% of Republicans, so that's our probability of Republican. And we can compute the individual probabilities for each issue. For issue 1, these are the fraction of Republicans that voted yes, these are the fraction of Democrats that voted yes, and so on and so forth. Now, using these probabilities, we can classify new data. So here you see an example where this representative voted no, then they were absent, then they voted yes, and so on and so forth. Realize that they were absent for the 2nd and the 16th vote. We're just not going to include this. We're going to assume as if we only had like the 14 other votes and just apply the formula that we just showed, which works perfectly well. So when we apply the formula and we plug in all our estimated probabilities, we see that the probability that this representative is a Democrat is extremely high, and they were indeed a Democrat, and here I have highlighted in bold the votes for which they agreed with most of the Democrats. Okay, and as you can see, essentially the model is aggregating all of these probabilities and realizing that the votes align more with the Democrats, and that's why it produces such a high probability of Democrat. Now let's take a look at the other generative model where we make a very different assumption to overcome the curse of dimensionality. We're going to apply Gaussian discriminant analysis to these two continuous features that are the volume of the entorhinal cortex and the volume of the hippocampus. What we're going to do is we're going to model the conditional distribution of the features given the class as a Gaussian. So here I'm showing you the center of the Gaussian for the healthy people, and also the contour lines that are determined by the covariance matrix that is estimated from the data. The center of the Gaussian for the Alzheimer's patients is here, and these are the contour lines that are estimated from the covariance matrix that again is obtained from the data. So just to be clear, we're fitting a Gaussian here, and we're fitting a Gaussian here. Great. So now what do we do with these Gaussians? We again apply Bayes' rule, which is exactly the same thing that we did in Naive Bayes. But now here we have a density because these are continuous features. And instead of assuming that they're conditionally independent given the class, we're going to assume that they're Gaussian given the class, so that we only need to estimate the means of the Gaussians for each of the different classes and the covariance matrix of the Gaussians for each of the different classes, which is going to be much more tractable than trying to estimate the whole joint conditional distribution of the features given the class. And these are the probabilities that we obtain applying that formula. These are the contour lines. So here the probability of Alzheimer's is 0.75, here it's 0.5, and so on and so forth. We see that the probability of Alzheimer's is higher here, and the probability of being healthy is higher here. So the model correctly identifies that smaller brain regions correspond to Alzheimer's patients. If we constrain the two covariance matrices in our model of the features given the class to be exactly the same, then we obtain contour lines that are linear. We actually obtain a linear classifier, which is usually called linear discriminant analysis. Now let's move on to discriminative models. The goal here is to approximate this conditional PMF of the class given the features directly, not as in generative models where we estimated the probability of the class and then we have this generative model of the features given the class. We forget about all that. We say we just want to classify. We're just interested in the conditional PMF of the class given the features. End of story. And different assumptions that we're going to have to make because of the curse of dimensionality are going to yield different models. We're going to call the model parameters theta, and we will see in a moment the different structure that comes from different assumptions. We're going to cover linear models such as logistic and softmax regression, and nonlinear models based on neural networks and classification trees. So these parameters theta are going to be learned from the data in exactly the same way, or based on the same criterion, let's say, for all of the models all of the discriminative models that we're going to explain. And just to set the notation, we're going to have some examples. We're going to have examples of the feature vector and examples of the associated label. So this is saying that for the first example, this is the value of the features. Maybe I should use consistent color. This is the value of the features, and this is the corresponding class. For the second example, this is the value of the features, this is the corresponding class, and so on and so forth. And we're going to have n data points. So the question is, how do we use these n data points to fit a discriminative classification model? And the way we do it is we model the ith feature and the ith label as random variables, xi and yi. And now we maximize the conditional likelihood of the labels given the features. We want to say, okay, according to the model, what are the value of the parameters that make the observed labels most likely given the observed features? And let's see, in general, this is going to be intractable because we have n random variables, not intractable, but this is, we're going to have to make some assumptions to actually be able to fit the parameters to get a model that can be tractably maximized. I feel that I didn't explain that too well, but basically we need assumptions because otherwise this cost function is going to have too many parameters. Let's put it like this. And the assumptions that we're going to make are that the labels are conditionally independent given the features, and that, so just to be clear, we're saying that all of these guys are conditionally independent once we observe these guys. And we're also going to make the assumption that each label is conditionally independent from the remaining features as long as we see its own feature vector. Okay, so essentially we're saying we're only going to use, just going to assume that the conditional probability of each of the observed labels given its own feature vector does not depend on other stuff. Okay, so we have in a way like conditionally independent observations of the relationship between the features and the labels. If we apply these assumptions, then we obtain the following likelihood, which is this probability but interpreted as a function of the model parameters, where we have the probability that the model assigns to the observed class given the value of the observed feature, and we multiply this over all the observed data. Usually this is a very, very small number, so we take the logarithm to make sure that we don't have any numerical issues. This is okay because the logarithm does not change the maximum of this function. Maximizing the likelihood is equivalent to maximizing the log likelihood. This is the cost function that we're going to use to fit all of the discriminative models that I mentioned before. But some of them, especially the ones that get nonlinear and complicated, can be difficult to maximize. For some of them, this cost function can be difficult to maximize. In generalized linear models, we will see that this cost function is actually not too bad. The idea in generalized linear models is that we want to approximate the probability of the class given the features as a linear function of the features. But of course, in general, linear functions of some numbers are not going to be valid probabilities. They're not necessarily between 0 and 1. So the trick that is applied here is that we have a fixed link function that maps the linear function of the features, that is based on some parameters learned from data, to probabilities. In the case of logistic regression, this is achieved through a logistic function that we can apply to binary classification. In the case of softmax regression, this is achieved with a softmax function that can be used for multi-class classification. So this is the logistic function that we use for logistic regression. The idea is that we're going to obtain some kind of linear function of the features that is represented by this dot, here, and the logistic function is going to map it to some value between 0 and 1. And it does this no matter what value that linear function takes. So the parameters are going to be some linear coefficients that are going to be applied to the features plus some additive constant. All of that is going to go into the logistic function so that it gets mapped to a probability. The logistic function is fixed. What we're learning from the data are the linear coefficients and the additive constant. And we do that by maximizing the log likelihood, which happens to be concave. We do this, but does not have a closed form solution. We do this using iterative methods. Let's take a look at what happens when we apply this to Alzheimer's diagnosis. We learn these linear coefficients and this additive constant from this data, and that gives us this plane that can then be mapped to probabilities by the logistic function. Here you can see the different probabilities. The contour lines are linear because what is mapped into the logistic function is linear, and the model, just as in the case of naive Bayes, correctly sees that here the probability of Alzheimer's should be much higher than here. Now let's take a look at the softmax regression, where the goal is to perform multi-class classification. We do not only have two classes as in logistic regression. So here, the probability of each of the classes, given the observed features, is obtained by taking a linear function of the input features, and this is not just going to be one linear function. We're going to have one linear function for each of the classes, and then we're going to plug this linear function of each of the classes into an exponential and then normalize it by dividing it by their sum. This is going to give us a number between 0 and 1 that is going to be the estimated probability. We are going to plug this into the log likelihood given our dataset, and that's how we're going to fit these linear parameters and these additive constants. And we usually do this maximizing the log likelihood using iterative methods. Let's take a look a little bit closer at what the softmax function does for our example where we want to classify wheat seeds into 3 varieties depending on 2 features. Here I'm showing you the linear functions for each of the classes, 1, 2, 3, learned from data. So these are the parameters learned from data. And we're going to apply them to a case where the first feature is equal to -1 and the second feature is equal to -2. These are the values that we get. Of course, they're not between 0 and 1. In fact, some of them are negative. So what we do is we plug them into an exponential function. So this gives us non-negative values that are quite extreme. Like the negative ones become very small. The ones that are positive can become very large. And now we just divide by their sum to get the estimated probabilities. And what we see is that the value that was larger and positive gets mapped almost to 0, and the other two get mapped that one gets mapped almost to 1, and the other two get mapped almost to 0. So this softmax function is acting almost like a soft maximum, hence its name, softmax. This is the linear function that is learned for the Canadian class. When we pass it through the softmax, it gives large probability to the area where we have mostly Canadian labels. This is the linear function learned for the Gamma class. When we pass it through a softmax, it puts higher probability, close to 1, in the area where we see more Gamma labels. And unsurprisingly, when we take the linear function learned from the Rosa class and we plug it through the softmax, boom, it gives higher probability to the region where there are mostly Rosa labels. That was softmax regression. In softmax regression, we plug a linear function into the softmax. When we use neural networks for classification, we plug a nonlinear function into a softmax that is parameterized by a neural network. So this is a cartoon depiction of neural networks. Essentially what we do in neural networks is we interleave a linear transformation that produce some hidden variables. Then we pass the hidden variables through nonlinearities. In this case, these are ReLU nonlinearities, rectifying nonlinearities that only allow the hidden variables to go through if they are greater than 0. And then we combine them again using another linear transformation to produce outputs. These intermediate operations here are known as a layer. The layer can have many more hidden variables, and we can concatenate multiple layers to create a very complex nonlinear model. But at the end, we do collapse it into into a number of outputs that is equal to the number of classes that we want to classify into, and that's what's going to be plugged into the softmax. Okay, that's what gets plugged into the softmax. We want to the probability of class K given the features. We plug in here the exponential of the output of the neural network for class K, and we divide by the sum of all the exponentials when we plug the rest, like all of the classes, as we did for the linear function. This is maximized by a stochastic gradient descent on batches of training data, because the training data set is usually quite large when we try to fit neural networks. When we do that, I'm going to show you what happens if we do this for a simple two-layer neural network like the one I showed you before, but that has 100 hidden variables instead of just 2. The nonlinear function that we learn for the Canadian class it doesn't look linear at all, right? It's highly nonlinear, and this allows the network to fit the data extremely well. And this really shows you why you have to be very careful with overfitting for neural networks, because in this case it manages to fit every single point. It manages to give a probability close to 1 to every single point that is Canadian, as you can see here. When you look at the nonlinear output for the gamma class, it's even more intricate. And the reason it's more intricate is that when you pass it through the softmax, again, it manages to give a probability of 1 to every single gamma label and to avoid the non-gamma labels that are here in between. Of course, the linear classifier would not have been able to do this. And this can be a blessing or a curse depending on whether this then generalizes to held out data. So you have to be very careful about that. And this is finally the nonlinear output for the ROSA class, which again correctly identifies all of the ROSA labels. Now we're going to talk about an alternative approach to obtain a nonlinear classifier that is also discriminative. This classifier estimates the conditional probability of the class given the features using a binary tree. So this is a tree that was constructed for this same data set where we're trying to do seed classification. And the idea is that the tree partitions the feature space into disjoint regions. And let's take a look at what I mean by that. So if we look at, for example, this leaf here, and these disjoint regions are associated with each of these leaves. I'm going to show you which one we have for this leaf in particular. This branch of the tree is telling us that the area is smaller than 0.18. This branch is telling us that the area is smaller than minus 0.5. And this branch is telling us that the asymmetry coefficient is smaller than 0.31. So basically, we're in this region. And now we're going to have one such region for each of the leaves, and altogether they cover the feature space. And now we assign constant probabilities within each of those regions. How do we assign it? Where we look at our training set and we look at the examples that fall within that region. In the region that I just showed you, there's 35 examples in total and 21 are Canadian. So we're going to say that the probability of Canadian in that region is 0.6, which is 21 divided by 35. The probability of gamma is 0.4 because there's 14 examples labeled as gamma within that region. And there are no examples labeled as ROSA. So the probability of ROSA within that region is just 0. Now, how do we build the actual classification tree? Well, we build it iteratively, adding these bifurcations for each. In order to add a bifurcation, we have to choose a feature and choose a threshold. And essentially what we do at each step of fitting the tree is we add the bifurcation to one of the existing leaves that most increases the log likelihood that we discussed before. So it's kind of interesting that logistic regression, softmax regression, neural networks, and classification trees all use the same criterion, which is the log likelihood of the model. In the case of classification trees, you can replace log likelihood by gene index, but it essentially has a very similar effect. Okay, so basically the way this is built is by adding bifurcations iteratively to try to build the tree that has the largest possible log likelihood, given this greedy procedure where we add bifurcations one by one. A problem that classification trees have, just like regression trees, is that simple trees tend to underfit and complex trees tend to overfit. A very successful strategy to address this has been to combine multiple simple trees. We don't have time to go in detail into each of these strategies, but you have a video about this. The three main strategies to achieve this are bagging, which trains individual trees on resampled data sets generated via bootstrapping; random forest, which does essentially the same thing as bagging, but modifies the trees by when we add a bifurcation, only considering a random subset of the features in order to obtain more diverse trees that we can then combine; and finally, boosting, which trains complementary trees that fit residuals of previous trees, which are then scaled down to avoid overfitting. Again, more details are provided in the individual videos. The trade-off that we have here is that if we apply these methods, we're going to definitely greatly improve classification performance, but we're going to lose the interpretability of the classification tree, where we know exactly why we are classifying each, like the example, as the corresponding class, because it corresponds to that particular region. Once you start combining trees, it's much less clear. And finally, we're going to discuss how to evaluate classification models. We're going to focus on binary classification. In this case, these are the results of logistic regression on the Alzheimer's diagnosis task. We have the probabilities, so we know what probability has been estimated for each of the data points, and we also know whether these data points are actually healthy or correspond to healthy subjects or Alzheimer's patients. So given all of that, how do we evaluate how well the classifier performs? We're going to focus on binary classification, and essentially we have three options. We can threshold the probabilities to produce an estimated class for each of the examples, and then evaluate these binary classification estimates. We can also just assess the discriminative ability of the probabilities that were estimated from the model. How well do they separate between Alzheimer's patients and healthy subjects? Or we can assess the calibration of the probabilities. If we interpret the probabilities indeed as probabilities, how accurate are they? We'll see what I mean in a moment. Okay, so let's start with the case where we produce a binary classification estimates. In that case, we can use accuracy to compute the fraction of total examples that are correctly classified. We can also compute the true positive rate, which tells us what is the fraction of positive examples that are correctly classified. Perhaps we might be more interested in the false positive rate, which tells us the fractions of negative examples that are incorrectly classified as positive. Or we might be interested in the precision, which tells us among the examples that we have predicted as positive, how many of them are indeed positive, how many are correctly classified. We can also use other metrics that combine some of these. For example, the F1 score is a combination of the true positive rate and the precision using a harmonic mean. Let's get a bit more intuition about what each of these metrics captures. Remember that in order to apply these metrics, we have to have binary classification estimates, and the way we obtain them typically is by thresholding the probabilities. So to the left of the threshold, we would estimate a 0, to the right, we would estimate a 1. If we use this threshold here, you can see that we are on the left, we do not have a lot of false negatives that are positive examples that are predicted as negative. Here, by the way, positive as Alzheimer's, even though it's not a very positive thing, but we're just considering that Alzheimer's is a 1, let's say. However, on the right, we have a lot of negative examples, so a lot of healthy individuals that are classified as having Alzheimer's. You can see them here. If we move the threshold to here, then these guys are not incorrectly classified anymore, so we're improving in terms of these false positives that we had to the right of the threshold, but we are increasing the false negatives, the Alzheimer's patients that are incorrectly classified as being healthy. And of course, this gets much worse if we use this threshold on the right. So there's going to be a trade-off when we utilize different thresholds. And to show you this, let's take a look at all of these metrics for the different thresholds. For accuracy, the threshold on the left is pretty bad, but the one on the right, the two on the right are actually quite similar. In case of true positive rates, this tells us among the examples that are truly positive, how many are we finding? Well, if the threshold is very small, we're finding almost all of them. As we move the threshold to the right, we're finding less and less. The false positive rate tells us how many negative examples are we incorrectly classifying as positive, and this is a lot when the threshold is too small. It gets reduced as we increase the threshold. The precision tells us among all of the estimates that we classified as positive, how many of them are truly positive. Well, if we put the threshold too low, we're making a lot of false positives, so the precision is actually pretty small, and it increases as we move the threshold to the right, because when we classify something as positive, we're pretty sure it's going to be positive. It's difficult to choose among all of these thresholds, but you could maybe apply the F1 score that has balances the true positive rate, or combines the true positive rate and the precision, and it seems that this intermediate threshold might be a good choice. So now let's compare the true positive rate and the false positive rate. Notice that as we move the threshold to the right, the true positive rate always decreases, and as we move the threshold to the right, the false positive rate also decreases. We can actually plot them against each other in a curve like this, where here both are very low and here both are very high. Ideally, we would want this guy to be very high and this guy to be very low. So we would want this curve, as we move the threshold, to be very close to that corner. Equivalently, we would want the area under this graph to be as close to 1 as possible. Well, it turns out that that area, which for our example is 0.847, is equal to the concordance of the classifier, which tells us the fraction of negative positive examples, such that the estimated probability for the positive example is higher than for the negative example. So this is a measure of discrimination between provided by the probabilities that does not depend on the threshold. Realize that this is about the probabilities. It just tells us how often the estimated probability is going to be higher for a positive example than for a negative example. How well does the probability discriminate between the positive and negative examples? And that's why this metric is a standard metric to assess the discrimination ability of a classifier. Sometimes we not only care about discrimination ability, we actually care about being able to interpret the probabilities produced by the classifier. What do I mean by that? So here I have separated, for this same Alzheimer's example, the estimated probabilities into bins. Here I've put all of the people whose estimated probabilities were between 0 and 0.1. And you see that most of them were healthy, which is good news. Here are the ones that had probabilities between 0.1 and 0.2, and so on and so forth. Now consider, for example, the patients for which the probability is between 0.5 and 0.6. We would want, if the estimated probabilities are accurate, if we look at all those patients that were assigned a probability between 0.5 and 0.6, we would think that roughly half of them should be Alzheimer's patients. This would mean that this estimated probability is close to the empirical probability that we observe in the data. We can actually plot these estimated probabilities against the empirical probabilities in a reliability diagram to determine whether these estimated probabilities indeed correspond to the empirical probabilities, and the closer we are to this line where they are equal, the better the model is calibrated. Of course, if you only care about calibration, you might end up with a model that is not very discriminative. The Breyer score evaluates both discrimination and calibration and is often used in forecasting. All right, so what have we learned? We have learned that there's two main strategies to build classification models: generative models, which include naive Bayes and Gaussian discriminant analysis, and discriminative models that include linear models such as logistic regression and softmax regression, and nonlinear models such as neural networks and tree-based models. And finally, we have learned how to evaluate classifiers using several different metrics that capture different properties. And that's all I got. Thank you very much.